예정입니다. 마이크폰
Okay. 제가 영어로 발표하겠습니다. So my research is on the electrochemical characterization of polyvinyl alcohol ceramic composite separators for supercapacitor application.
한번 좀 보여주세요.
클릭하는 안 돼요. Okay, so supercapacitor components made up of four main parts. There's a current collector, the electrode, the electrolyte, and the separator. For the electrode we use activated carbon, and the electrolyte we use 6 molar KOH, and the separator we use polyvinyl alcohol and ceramic composites. And basically we use different types of ceramic particles mixed in with the PVA to get a composite. And the ceramic particles we used was alumina, silica, and titanium. PVA, the reason why we use PVA is because it's cheap, and widely available, it's biodegradable, so it's very environmentally friendly, and it's easy to produce thin films, so it's easy to manufacture, and it's also easy to experiment with. And when you put it in aqueous solutions, it becomes plasticized and tear resistant and very stretchable, so it's a very safe alternative for supercapacitors. The reason why it's not used often is because it has very low ionic conductivity. And the goal for my experiment is to mix the different ceramic particles to increase the porosity by creating more amorphous regions in the polymer matrix. And hopefully this strategy can also be used for other types of separators as well. The aqueous electrolyte that we use, most commercial supercapacitors use organic electrolytes because that has a much wider potential window, giving it higher energy density. And the reason why we use aqueous electrolyte is because it creates more ionic interaction, preventing the PVA from dissolving into the water, and it also has higher ionic conductivity. This is the manufacturing process that we use to prepare the PVA ceramic separators. You mix the ceramic particles and the PVA into water, and you heat it at 80 degrees Celsius, and you soak it in ethanol for 24 hours. And what it does is it reorients the different polymer chain end bonds, the OH bonds, with the hydrogen bonding with ethanol, and this will give you a nice thin film like this. And when you dry it at 60 degrees, it'll give you a nice separator that you can use. Here's a scanning electron microscopy that we use for morphological characterization. With the PVA separator, you don't see as much porosity as when you add ceramic particles. And what it does is it creates amorphous regions by breaking the crystallinity structure, and this will hopefully increase the ionic conductivity by creating more pores. We did some stretch tests to see its tensile strength because we were afraid by adding the ceramic particles it'll weaken the polymer structure. But as you can see, not much structural integrity is lost. So adding ceramic particles is a safe alternative for increasing ionic conductivity. We did an ionic conductivity test with 2 nickel plates in a pouch cell, and you can see that by adding ceramic particles you can increase the ionic conductivity over the bare PVA separator. In the cyclic fault tomograms, you can see that the capacity, especially at high scan rates for the silicon and titanium, were much higher than the PVA, and showing that it has much higher rate capability compared to the PVA separator. This is from 0 to 1.8 volts, and you can see the same thing. At high scan rate, it will have much higher capacity. I compared all the different PVA separators at 100 millivolts per second, and TiO2 at a low scan rate. TiO2 has a much higher capacity than the other separators. These two graphs are the capacitance at different scan rates. you can see that the silica and the titania separators have much higher capacity than the PVA separator. And this is the cycle performance. So our research was to show that by adding ceramics to PVA separators, you can enhance the electrochemical properties. This is because the ceramic particles create more amorphous regions, increasing the porosity in the polymer matrix. The higher porosity means ionic conductivity is increased, which means higher capacity and better high rate performance. And these electrochemical enhancements can be achieved without any loss in structural integrity, as you can see in the stretch test, even though they have more porous morphology.